Hello, welcome back. We're now going to talk in a little bit more detail about this final, fundamentally nonlinear behavior, that of multiple equilibria. And we're just going to dive a little bit more deeply into the specific example and also try to explain why this is something that cannot be displayed by linear systems. And just to remind you a little bit, this property of systems having multiple equilibria can be very useful in practice, for example, in the designing of memories for computers. So there you want to have a device that can store either a 1 or a 0, and one very natural way to do this is to have a system with an equilibrium point corresponding to 1 and a separate, distinct equilibrium point corresponding to the 0. And then depending on whether you want to store a 1 or a 0, you just apply some inputs to push your system into the corresponding equilibrium point, or push it out of the corresponding equilibrium point. And also just a little reminder that the example I'm going to go through here, well, you can go and play around with this for yourself. Go and build the Simulink model. We've got a little template for you, and then you can try it out in different initial conditions and sort of see what happens. So without further ado, let's get on with the example, and it's going to be a sort of a slight variation on the mechanical model that we used for the Van der Pol oscillator, but rather than putting nonlinearity on the damper like we did there, we're going to put nonlinearity on the spring. So just to flesh that out a little bit, just like last time, we've got our ceiling here, and from this we hang a spring and a damper, and they're connected to a mass, and the mass has position q measured relative to some fixed reference frame, and we also have an external force being applied to the mass. Just like last time, we're going to ignore gravity. We could include it, it just makes things a little bit more messy, and in fact even if we include it, we'll still end up with a system with 2 equilibrium points. So just for simplicity now, gravity is gone. Sorry Newton. So let's just flesh this out a little bit more. So we said we're going to have a linear damper this time, so the damping coefficient is just going to be c, but we're going to have a nonlinear spring constant. In particular, our spring constant is going to be a function of the position q, and in fact the nonlinear relationship is going to be precisely the same as the one that created the Van der Pol oscillator. It's just this time the nonlinearity is on the spring rather than on the damper. So we're going to say the spring constant is equal to mu, and then we put our q squared minus 1 in. And because this is so similar, it's easy to put into our state space form in exactly the same way that we did for the Van der Pol example. And if we do that, we end up with the following nonlinear differential equation in our standard form. So we have d by dt of our state vector, which, if you remember, consisted of the velocity and of the position. And this was equal to 2 things. And the first thing, well, the bottom equation, d by dt of q dot, when written in terms of our state, well, q dot is in our state, so we just put it in here. And the top equation, this was our Newton's law less gravity, and so we just list out the forces applied to the mass here and divide them by m. So we have this external force F, and then we have 2 additional forces, one from the spring and one from the damper. The damper this time is linear, so this is given by c q dot, and again divided by m. And now we have the nonlinear spring force. So the nonlinear spring constant is mu q squared minus 1, and this is all multiplied by q, and we divide through by m. And here we have our ODE in our standard form. This is our x, and this is our f of xu. Everything in this side is either constants, inputs, in this case the force, or part of our state vector, in this case the q dots and the q's. And if we wanted to define particular outputs of interest, we could just define our g equation through that. So suppose we're interested in the position of the mass, then we just say y is equal to q, and this is also of the form g of xu. Everything just depends on entries of the state and entries in the input. Okay, great. So what happens when we simulate this system for different initial conditions? And we'll just draw out some solutions. Again, go away and play around yourself if you want to see this, well, kind of in action. So we'll draw ourselves a set of axes just like before. So here we have time, here we have the position of our mass q, and again we're going to assume that all of our external forces are equal to 0, and we're going to have an initial condition with 0 velocity and some nominal displacement q0. So this q0 just corresponds to like pulling the mass down or pushing the mass up and letting go, and then because we're not applying any external forces, it just sort of bounces around and does whatever the dynamics tells it to do, and we just see what happens. So if we go ahead and simulate the system, what does happen? Well, it turns out if we start with an initial condition, say here, so this is some nominal displacement, so we pull our mass down by a little bit here, we let go, and the mass goes and follows a trajectory, something like that, and it settles down. So this is q of t, and it settles down to a value of 1. And this is a bit weird, and it sort of shows some weaknesses with this mechanical analogy, if you like. So I pull this down, and what this is saying is that it's going to come even further down and settle down to some equilibrium displacement like this. Maybe it doesn't make a lot of sense in the context of mass spring dampers, but you could certainly imagine trying to design, say, electrical components or all sorts of other things to have an analogous behavior, but where we could actually build this and, say, implement our computer memory. So that's what happens if we start with this initial condition. What happens if we start with another one, say, up here? So we take a big, initial displacement and we let go. Well, we settle down to the same equilibrium point. Okay, so no real surprises so far, and nothing to tell us that this has anything to do with nonlinear systems, actually. We know linear systems can have equilibrium points. Okay, it's slightly weird that the equilibrium point isn't 0, but we could certainly, just by shifting all our variables around, end up with a new system where q's were measured relative to this value of 1. Then we would have our equilibrium at the origin, and it looks like everything's settling down to this equilibrium. So, like, why is this some kind of nonlinear behavior? Well, we only start to see that when we try negative initial conditions. So this corresponds to taking our mass, pushing it up a little bit, and letting go. And if we do that, well, we get this sort of mirrored behavior. So if we start here, we in fact go down, and then we oscillate a little bit, and we settle down to a value of -1. And now this is beginning to look really weird. So we have a system that, depending on our initial conditions, it will settle down to one equilibrium point or another equilibrium point. And you go away and you try various other points, and you find that if I start anywhere that's negative, I settle down to this -1, and if I start anywhere positive, I settle down to this +1. So we have a system that seems to have two distinct equilibria, and this was precisely the behavior we were interested in trying to describe and understand, because now in our computer memory we have an equilibrium point corresponding to, say, storing a 1 and corresponding to, say, storing a 0. And we can flip between the two by, maybe, we haven't considered applying forces here, but we apply some force to push us up, and if we get far enough up, then we'll converge to our other equilibrium point. So by adjusting our inputs, we could apply a few inputs to push us from one equilibrium to the other, corresponding to storing different things. Okay, so that's kind of cool. We've got a system with this multiple isolated equilibrium behavior, but why is this something nonlinear? Well, hopefully you can already see this, that our two properties of linearity, namely superposition and being able to scale solutions, makes it impossible for a linear system to have multiple isolated equilibrium points. Maybe it's easiest to see this just with the scaling property. So just by scaling our initial condition by a factor a, if the system was linear, the output must also be scaled by that corresponding factor. So what that would mean is, if we had this initial condition as we scale it, our output must be similarly scaled. So if we make this 10 times bigger or something, so that our initial condition is here, if linearity held, the output trajectory would just be 10 times this one. So we'd end up with something going down here and settling down to an equilibrium that was 10 times as big. And this is not what happens, but why does this actually show more and show that linear systems can't have isolated equilibria? Well, we now just imagine that we vary this scaling, and for every scaling we get a new equilibrium point. So for every scaling of our initial condition, if the system was linear and if it had multiple if we wanted it to have this property of multiple equilibrium points, well, by this scaling property, we'd actually have to have a continuum of equilibrium points. We couldn't possibly have isolated equilibrium points. And that's what makes this a nonlinear behavior, the property of having isolated, distinct equilibrium points. And that was why it was useful. It would be a fairly useless computer memory if it just settled down into this continuum of equilibrium points. So if we made some small error or things knocked our system around, we could easily have the memory pushed into a completely new value, and we wouldn't be able to work out what it was that we were trying to store. So there we have another nonlinear behavior. And I don't want you to think that this is the end of the story for nonlinear behaviors. Certainly limit cycles, regions of attraction, multiple equilibria, they're all very interesting examples of nonlinear behaviors. But in fact, there are many, many more out there for you to go and investigate. Some of the most exotic and exciting ones are chaos and these so-called strange attractors. We're not going to focus on them very much in the course, but I mean, there's all sorts of great lecture and learning material out there. Go search on the internet if you're interested, and I'll try and maybe provide a few extra links to this type of thing. But that's it for our introduction. We're now going to get our hands dirty and start trying to come up with tools and methods for understanding these nonlinear behaviors and how we can design for them or get rid of them if we don't like, and that kind of thing.